Thank you. So this is Tracing Struct Accesses with Struct Stalker, a journey into the darkness of LLDB scripting. But the sort of secret name of this talk is LLDB Considered Painful. So I'm Jeff. I work at NCC Group, and I hack on all sorts of random things, and I do terrible things to technology and thoroughly enjoy it. So this talk is kind of going to go really fast, but I'm going to sort of start with some background on what led to this work, demo a tool, and talk a little bit about it, and then kind of dive straight into the internals of LLDB stuff related to scripting. So a while back, I was doing some stuff related to libfuzzer. If you didn't know, it is essentially sort of the LLVM project's AFL, except with the sort of idea that you have an entry point, and then you take the fuzz data, you pack it into structs and objects, and then you pass those into library functions so that you don't have to deal with standard in, standard out. But if you want to fuzz anything that's more complicated than basic library functions and utilities, you kind of have problems because a lot of internal functions that may do a lot of important stuff that you'd want to get at, they take very fancy context objects that may have like hundreds of fields, and they may only use a few of them, and it's hard to tell what you need to fill out with fuzz data and what you need to fill out with legitimate data so that the thing actually runs and doesn't crash. So basically the problem is what fields are actually used and needed. How do you figure this out? So you try to profile the accesses, but for things like GDB, LLDB's memory watch points, they're not really useful for this because they're limited to size of single values, like 8 bytes, and then there are a number of limitations related to how many you can have at the same time. So some related work was done by a coworker that I helped a little bit with, named Nick. He basically wrote this thing to help him reverse engineer video games, and he would essentially he would be able to find values like coordinates on a game map that he was interested in, and he wanted to try and use those to find the global context object for the entire game. And so we basically kind of put together this design of an architecture that would trace all of the instructions, and then it would place guard pages over where the interesting data was. And every time a page fault was hit, we'd catch it in the debugger automatically, and then process the entire backtrace to find out who was doing the accesses all the way up the chain, and rinse, wash, and repeat until we got ourselves to the global context object. In this case, though, we're going from the top down. We don't need to go from the bottom up. So it's a little bit simpler to write. I had put together a basic proof of concept at one point that just used mprotect and just got like one value into the original struct. It didn't really go any deeper, though. Then I did a rewrite. So I'm going to go into that rewrite, which I call Struct Stalker. It is a magic LLDB Python script, primarily targeting Unix, which really means Mac OS and Linux. You generally configure it with calls to target, so you keep calling it over and over again until you tell it to start, and that configures it. Basically what it does is it sets breakpoints at functions that have variables that you want to hook on, and then it uses mprotect to lock the pages that those variables are in, and then it catches the page faults, undoes the mprotect, steps a single instruction, then reapplies the mprotect, and over again until it's traced all of the accesses. So a little bit of demo. So in this code here, what's essentially happening on the upper right is just setting up Struct Stalker to stop at the function bar and then track the local variable t. Then afterwards, we tell Struct Stalker to start, and it passes all of the remaining data as arguments to the process. So this takes a while, mostly because when you are tracking a local variable on the stack, that means that any time you call a function or manipulate the stack for anything else, you're arguably going to hit a page fault, and then you have to process it. And processing all the page faults is slow, but this doesn't really need to be performant, as I just need to find all of the values once and then write some fast code that does fuzzing in memory. So you can kind of see some of the constants showing up, although depending on where you're looking, they might show up in reverse order because of endianness. But you see the 41, 42, 43, 44. Then there are some other values. I'll skip a little bit ahead. We can see the 42, 42. And then at the very end, we can see the 41, 41 from bar 2 that was called at the end of bar. And all of these involve a bunch of accesses that essentially, there we go, were tracing fields that were being set onto an object and then locking those pages and recursively following it all the way along the chain of execution. This has some limitations. Pretty much this is something you can only use if you have source code. There are a couple of shenanigans you can play if you don't have source code. But if you're using libfuzzer anyway, chances are you have source code. It will be up here soon enough. I need to remove all of the printf debugging and stuff like that. I'd like to thank a couple of people for kind of inspiring this work. Brian McFadden helped me work on the initial proof of concept that just kind of did the one level instead of recursive. And then Nick Collison is the one who wrote PSR. So is this it? No, the talk goes on. But first, I'd like to take a brief moment to remember a former coworker who passed on this year. He was an asshole, but he was our asshole. And Jim is sorely missed. So now, less somber, more rage. So LLDB, why? So LLDB is sort of fairly big. It is kind of the new debugger on the block based as part of the LLVM project. It's a big competitor to GDB, and it is going multi-platform in ways that GDB never really intended to. It even has Ubuntu packages at this point. It is pretty scriptable. It was a core focus of it in the first place. So LLDB is basically the backend for Xcode. So that tells us that all of that fancy GUI stuff works, which means it has to have some underlying stuff that works, that we can access, hopefully. And it supports, raw binaries, but also, source-level debugging for your typical smattering of native languages, and anything that puts in dwarf debug symbols. So, like Rust also works on LLDB if you build debug builds, or not, but then you won't see your code. It supports a bunch of platforms and has Python, which is great. So I'm going to talk a bit about the CLI, just because it's necessary to cover some of the CLI functionality so that we kind of understand where the Python implementation that underlies the CLI actually kind of comes from and why it works that way. I'm going to skip over a lot of things just because they're not strictly necessary for the talk, but I feel it's useful to provide sort of tips and tricks that you learn along the way in your slides. The slides will be available, and there's a whole bunch of extra information I have at the end of the slides that I'm not covering that includes all of the magic numbers and things that you're going to need if you want to do anything fancy. So with that, though, I'll start that the first most important command that you could ever run in LLDB, and that should be at the top of your LLDB init script, is that you set the x86 disassembly to Intel syntax. AT&T syntax is sinful. And then the next important thing is that if you're on OS X, you want to make sure that you completely reset your path to the defaults, because if you're using an alternate Python that you get from Homebrew, things are probably going to break and you're not going to know why. Your plugins are going to start failing. You're going to get a ton of warnings about why the 6 module doesn't work. Just bad vibes. So the first command we're going to talk about is process. It's basically the thing that manages attaching to processes and connecting to remote debug servers. And then it's the thing that basically what runs through to actually start a process and load it. The most important option is -s. And that's because when you attempt to set breakpoints by address before you've actually run the process or loaded it, really, they don't work. They just don't work. Address breakpoints do not work in LLDB by default, which is just the most ridiculous thing ever. So what you need to do is you need to break at the entry point so that the binary is already loaded and then set them. This breaks a couple of things elsewhere, but I have ways to get around them. Disassemble, I shouldn't need to explain to a bunch of people at a reverse engineering conference. Breakpoints, the only thing useful here for our purposes about breakpoints is that you can set them to call Python functions by default when they get hit. Threads are primarily useful for calling the stack trace, getting the stack trace out, which you use with thread backtrace. And then additionally, switching threads. So threads are basically groupings are used to manage themselves, but also get access to the frame stack under them. And so you want to select the thread that you're going to use to do frame operations. And LLDB has a concept of current that doesn't necessarily mean active. So the current means the one you're actually wanting to work on, not the one that actually is like running or focused. Frame is basically the command you use to deal with the stack frames. You can get information out of them, but pretty much that's redundant because you're going to get that out of thread backtrace, which calls into frame anyway. Variable is the more important thing here because that's what lets you get access to things like registers. Memory is used for scanning memory, reading memory, writing memory. The only weird thing about it is that if you attempt to read memory out to a file, it doesn't actually clear the file before writing to it, so you should be careful about that you don't have separate reads clobber each other in the same file. Target does a whole bunch of magic and is a thin wrapper over process, so it actually manages setting the debugging target, loading things. It's pretty much focused on loading binaries into memory and parsing them. So with that, the more important functions of the many are related to dumping the memory mappings and symbolicating, getting your symbols and things. Expression is a very fancy capability that allows you to essentially execute C code in the target process. It will JIT the code, inject it in the process, and then jump to it. But you can do other things than just C. You can set several languages that it supports. Technically, it supports C, C++, Objective-C, and Swift. But if you use the launch with -s, you get this problem where your linked libraries haven't actually loaded into the process yet. So on OS 10, you're going to want to wait until this dilib bootstrap function finishes, and then you can start doing things. So one of the limitations about expression is that it doesn't really work for things that aren't in the binary or if the binary is stripped. However, there are ways to get around that. So normally, you can't really run Swift expressions in a binary that doesn't already have Swift loaded because it needs to use the Swift runtime. So the way that you can get around this, of course, is you just inject the Swift runtime directly into the process, and then you can run Swift code for whatever reason that you might want to. But this applies to running libraries that aren't necessarily in the binary. LLDB uses Python 2 on pretty much all the platforms except for Windows, where for some godforsaken reason it uses Python 3, the fools. It's a really thin shim on top of C++. Basically, they just use the Swig FFI to auto-convert all of their C++ code into Python, and basically your Python code looks and runs like runs like C++, except you have no type safety and everything is floating around with duck typing, which is problematic and doesn't make anything faster. You're probably better off just using C++. But they don't really make that easy. It's really buggy to use because of the thin layer on top of C++, because the Python API doesn't really properly handle the scopes of lifetimes of the objects that are actually in C++. So the Python handles may remain after the objects are actually freed, which is problematic to say the least. The CLI commands are implemented in a mix of Python and C++. They're mostly in C++, but technically they can call out to Python, so that led to some weird design decisions in the internals of LLDB. And the documentation, unlike the CLI, is really bad. The CLI has really great documentation. It has like tab complete. It's just, the problem with it is that it's just super verbose and it's so many characters to type. But the Python API, which is basically the C++ API, has essentially no documentation. They have really large, like Doxygen type style documentation, but the functions that actually do have explanations under their names pretty much just say what the really, really long function name says. And many times that's misleading. And other things they don't tell you about are like what the return value is. So if it looks like a number, it might be one of three things. It might be a numeric, it might be an integer in Python. In that case, you're lucky. More often than not, it's a string. If it's a string, it's often hex, but sometimes it's base 10. Why? It is a mystery. But it's consistent. So the same API will return the same type of thing always, just different APIs will do different things, and you won't know which is which until you try. The way that the API works is kind of weird. So the Python API is basically the entire public part of the LLDB C++ code base, which wraps the internal part of it. But there are a lot of really useful functions in that private part that you can't really access from the public part, and I have no idea why. And it just makes things more annoying because you have to go to shenanigans to get around to deal with them. So there are like hundreds and hundreds of these classes and things, but the ones that are important are the ones that are on the screen. The breakpoint and everything that's in the public API is prefixed with SB. And so everything is like SB, but I'm just gonna say their names because saying SB before everything is just tedious and annoying. So breakpoint stuff is for managing breakpoints. Debugger is pretty much your main interface. It's the only thing that you can trust to represent reality. It's how you get a handle on everything else, and everything else, once you've done something with it, can go away. So most of the time, you're just going to want to keep going back to the debugger to get a fresh handle on the rest of the objects. So the target manages all the target stuff, process manages all the process stuff, and so forth and so on. The only interesting things, though, are that the process is actually iterable as a batch of threads, and threads are iterable as a batch of frames. But frames are a grab bag of registers and variables, so they're not exactly super iterable in the same way. Then you have a bunch of classes that you're going to need to actually do anything useful. So stream and error are these objects that you basically pass into the APIs to get output, because it's C++ and they want you to pass in an object that does its own memory management instead of them doing memory management. Broadcaster, listener, and event are the things that you're going to use if you want to make an event loop. And command interpreter is the thing that you use when you just want to run CLI commands because dealing with the Python API is too much of a pain. And then command return object is what you need to get the string output from that so that you can parse the string to actually get the value out. So your entry point when you run some LLDB code is basically you're going to do command script import. You're going to give it the path to a script. Generally, you put a bunch of these in your LLDB init file, much like your GDB init file. And then you have this magic entry point called __ LLDB init module that gets a couple of things. It gets basically this debugger object, and then it gets this dictionary that is completely useless. Debugger object is the one you want. You can use then the global LLDB module that's basically magic to then register up commands. And then when they run from the command line, they call into the function itself. And so in this case, it'll be the my command handler. And it gets a couple of parameters. The ones that are useful are the debugger object, the command line, which is just the whole string of it. Nothing's tokenized for you. You have to parse your arguments yourself. Then the sort of result object or return object that you're going to put a response code into. And then the same internal dictionary that is completely useless because you have access to globals across all of your stuff running. It's probably a holdover from for backwards compatibility. So the way you set breakpoints is you do them through the target API, which is how they're actually implemented. You can do them by name, you can do them by address. You have the same limitations with how you'd run them, where depending on how you start the process, if you do it by address, you'd need to worry about -s. You can set them to run only once, and then you can set the callback function. But the weird thing is that you set it as a string relative to the file name that already has to be a module that's loaded, instead of just giving it the function. But when it eventually hits and runs, your callback function gets past a frame. It gets past this breakpoint location object, which pretty much tells you just kind of where the breakpoint hit. And then that same useless shared dictionary that you don't want to touch. The problem with the frame, though, when passed to the callback, is it actually has a lifetime. If you keep that thing alive after the callback returns, you're going to get use after free, you're going to get a double free. Things get really weird. And the worst case that could ever happen is that things continue to run, of course. But there's also other problems. So the callbacks actually run concurrently with any code that you might have in the background that's attempting to run and manage the debugger loop. This leads to significant levels of non-determinism, which is really bad for scriptable debugging. LLDB plays fast and loose with the Python global interpreter lock. CPython is not thread safe internally, and so only one piece of Python code is supposed to be running at any given moment. LLDB, because there's the potential for native code to call back up into Python, it releases the lock every time you call an LLDB function, and every time it returns, it takes the lock again. This leads to problems where essentially you can have your Python code interleaving and leads to all sorts of race conditions in LLDB itself and the Python code. So Python doesn't crash, but LLDB does, because LLDB is still not really thread safe internally. There are a whole bunch of places where they don't properly take their mutexes and the like, and things crash constantly if you're not careful and not managing things properly. So alternatively, you can just throw everything away and say, I'm going to just run the CLI commands where everything is nice and safe. And you do it kind of like this. You'd get your hand on the command interpreter object, you'd pass it a command, and then you'd have to parse the string output. Alternatively, if you don't want to have to parse string output, you could just use the real APIs. And so in this case, it's target evaluate expression, and then you just get the value out, and that's an integer. mprotect is kind of special as a syscall because if we're trying to track pages, but we're also trying to track the frame that is like currently executing, such as like local stack variables, we can get to this weird position where the syscall gets performed by the kernel, but then it returns back to user space, but then user space tries to return from its stack frame. Unfortunately, its stack frame is in the middle of a page that is now no longer read, write, execute. And so normally this is like fine, if someone were to write such code themselves, you could debug it. But because of the way that LLDB generates the code to like make the calls, the whole thing gets locked up real bad. And so what you actually have to do is you have to modify the stack pointer itself, shift it down a whole page, then do the mprotect, and then shift it back. And that lets you avoid this problem. The one problem with this is that anytime you start modifying the stack frame or the concept of what the stack frame is, LLDB magically invalidates all of its frame objects. So you need to get the frame again at the bottom. Now we get into the advanced scripting section. That was the simple stuff. So LLDB only actually supports callbacks for breakpoints, not even watch points. And it certainly doesn't do it for other kinds of debugger stops. So we actually need to take control of the entire loop to process those events. And there isn't much code that really does this in the wild. The only code that really does this stuff is LLDB itself. And some of that code is just unit tests that don't exist to run the code, but exist to like check failure cases. So the broadcasters basically are any type of object that like actually does stuff and determines that some sort of state event has changed somewhere. And then it fires off an event to anyone who is registered on it so that you can rely on the broadcaster to do the fancy processing for you. There are a couple of them. They are completely undocumented, but these are the names of them. These are the different types that I pulled out of the code base. They align pretty well with the magic objects that I said are super important before. You've got your target, your process, your thread, and your command interpreter. Communication is actually what gets used whenever you're dealing with a remote debug server. But none of these are debugger. So the debugger is actually just a thin shim on top of SB command interpreter itself, actually, which actually runs the entire UI of just when you type in like LLDB. That's all actually just a command interpreter. So listeners are these sort of waitable objects that are registered to these broadcasters. You can ask them to just wait until they get an event. You'll block, everything will continue in the background. You'll get an event eventually, and then you get to process it. So the way that this code actually works properly, and the only real example is in the code base itself, where debugger itself manages its own event loop. And so since we sort of need to be a debugger to manage this, we do what they do, right? So they register their listener to just the process thread and command interpreter, but not anything else. It's a little weird. Then they loop on getting the events. Then when they get the events, they compare them to see which actual broadcaster emitted the event, and then they get some metadata out of the event and then attempt to handle it properly per the special functionality of that. So, as the good saying goes, good artists copy, great artists steal. And we have, always been shameless about stealing great ideas. So basically, this is pretty simple to do, although it's pretty undocumented. The documentation does not tell you anywhere that you're supposed to get a handle on an existing broadcaster. It almost makes it seem like you're supposed to create your own. This is wrong. You could do it. It just won't do anything useful. So basically, you create your own listener, and then you get someone else's broadcast receiver. So we get the broadcast receiver from the process. Then we add our listener to it, and then we start looping in an infinite loop. The first part of this actually is a check to determine that the process hasn't exited for some reason before we even started the loop, in which case we'll be waiting forever for events that will never arrive, and the whole thing will lock up. That would be bad. So barring that, we wait for events, and in this case, we just wait 1 second for event. It'll return early or it'll time out. If you want to make your event loop wait forever, though, you actually have to use uint32 max. You can't pass it 0 or anything. It's specifically uint32 max. That's documented nowhere. That's just a quirk of the C++ code. Then you attempt to determine that the event actually comes from your SB process broadcaster, and then you move on. Then you get the type of the event, and then you determine it's a type you actually want to handle. So in this case, we care about when the state we care about when the state has actually resulted in it stopping, and then we do some stuff. There are some issues though when you use the breakpoint callbacks, right? So we can't deal with this non-determinism crashing our process constantly, but we control the debugger and we know when it stops. So we can just implement our own breakpoint handler. And this took, it was hacky, but it took 30 minutes, an hour, and the LLDB people still failed to do it properly for years. So I don't know what they're focusing on. But basically, the problem with this is that different platforms have different kinds of error messages that happen when the process stops. So on OS 10, you get this exec bad access for page faults. Linux gets sig-seg-v, on and on. You need to handle these appropriately. And you also have to catch the signals for them so that you can then handle them. But that's about it. And once you do all of these things, you too can become the debugger and do as you please in memory. Before questions, I just want to make it clear, these slides also have a whole bunch of the magic numbers that you need for all of those events that are basically completely undocumented, and it also tells you where you can get more of them. They're kind of semi-documented with comments in the C++, but they're all pretty much understood if you read what they are. So are there any questions? Right there.
Okay, I guess I'll go first. With all of this mess, how tempted were you to actually just write your own bindings instead of using the existing Python ones?
So I haven't gotten to it yet, but what I actually kind of want to do is I want to just start using the FFI to start, or with C types or something, and just start mucking around and invoking this stuff internally in LLDB. The problem is that Apple's LLDB on OS 10 is kind of I think it's semi-obfuscated or something, or they strip the symbols, and things get weird. So I have to crawl around and kind of figure out where those hidden APIs are. And the reason for that is one of the things I showed was I was grepping to filter output. The command interpreter, so you can tell you can deregister listeners from broadcast receivers, or sorry, broadcasters. This is an Android. But the problem is that you need the actual one. There's an API that gets you the list of all registered listeners, but that's one of those private APIs. And so if I can get that, then I can start deregistering them, because otherwise, every time I break on one of my breakpoints that I set to then set the page protections initially, it will dump. It'll just print out the next 10 instructions every time to standard out, and there's nothing I can do. So the only other way around that is to just not use LLDB as the process, but to just use it as a library, because then that command interpreter won't be running. but I want to use this like from LLDB so I can just drop in every so often and do something.
Good morning. Thank you for your talk. Some of the bugs you described were kind of astounding, and I took an interest in I just went to the Bugzilla of them, and they seem to have the query capped out at 500 bugs that are years and years old. I was just going to ask you if, do you see a path forward here, or are you going to try and report some of these, or is there a point?
I mean, it's not like they're security bugs, although I did secretly have one of my bullets say that people should start fuzzing LLDB's processing from like the target process, because if they're that bad on this stuff that's just the basic functioning, who knows how they are on when they try to parse memory structures in a target process. But I don't. It gets better like going forward. It's just you gotta wait, and there's like then potentially the secretive kind of processes that go behind its main development team, and every so often a batch of that LLDB makes it to the public LLDB.
Thank you.
More questions? If not, thank the speaker.
Thank you for your time.